if the error is smaller than the tolerance, then we accept the solution. Of course, then it's good enough. But then we take the second solution, so that we have then we continue with the second solution, because that is number 2, because that is more accurate than the first one. So that is what I forgot to tell you. You can also allow here equal. So now, as already announced, we want to look into stability. First, into stability of the ODE itself. So, let me give you some background on that. Stability of an ODE. So now we are talking no longer at the moment about numerical solutions, but on an ordinary differential equation. So that depends on the Jacobian matrix of the right-hand side of the ODE, that is of f of Cy with respect to, with respect to y. So that means it depends, then this Jacobian is nothing but looking at the f of Ty with respect to y. If we have a system of ODEs, then f is a vector and y is a vector. So if we then do this derivation here, we get then the Jacobian matrix. So for example, take the first component f1, and first component is the derivation with respect to y1, second with respect to y2, and so on. So the first row and then so on. So we get a matrix by that. And what is important of this matrix is looking at the eigenvalues of it. So if the eigenvalues of this Jacobian matrix, f of Ty dy, if they have a negative real part, so the eigenvalues are complex numbers, so they can have a real and a complex and in imaginary part. So if the real part is negative, so that means that the real part of the eigenvalue lambda is smaller than 0, where lambda is an eigenvalue. Of this Jacobian matrix. Then the ODE is stable. So, what is that? Why is that important? Let's now suppose that we have an ODE with 2 different initial conditions. So suppose, and I will now use a different notation because I shall use the difference of the solutions later on with using the letter y. So now we write our ODE in terms of z. So we have an initial condition. In that case, we call it z0. And we have some other where we have a different initial condition. So that is 1. And we have another one where we call this z tilde. So the derivative is the same function at the same time, but we have a different solution because the initial condition is different. So that is the z0 tilde. And then we want to look for the difference. So that is the idea of stability. Look what happens if we have the same initial condition, to which solution does that lead. So then we have the difference, z tilde minus z. We take then the first derivative. We see then we get a difference in the right-hand sides with t and z0 and with t and z. And here we can use the mean value theorem now to get the derivative, or the Jacobian in that case, of t with some, I call it z star, it is some between z and z tilde with respect to z. So that is the Jacobian matrix again that we discussed already. That is then times the difference between the two solutions. Now we want to introduce the notation, therefore I say the letter y for this difference. So difference of two solutions is denoted then by y. So y is then the z tilde minus z. So then we can express this difference here, what we have then in this equation. So we get here the difference, derivative of that is then equal to this, if we call this here J, the Jacobian matrix is equal then to this Jacobian matrix J times the difference itself. So then we get something of this. And to get an understanding of that, we want to look at the scalar problem. What we do in reality is we would then get the eigenvalues, get the eigenvectors, and get that to separate scalar problems of the kind that we want to look at now, that we have in the scalar case. So for the understanding, it is sufficient to look at the scalar problem. And in that case, J is equal, then we have just one eigenvalue, it is the derivative of the right-hand side with y itself, it's just a number. That is would be then corresponding to what we call it then the lambda, would be just scalar value, and as we said before, it can be complex. So we allow it to be complex. So in that case, we can directly solve this equation. If this is y prime is equal lambda y, if we make the additional assumption that the lambda or the is constant. So in reality, it's also dependent, as we said, the z star is between z and z tilde. But if we ignore that, we assume that it's constant, then we can get immediately a solution. Solution of equation, let's see, that was equation 1, is then the following, that is now 2, solution of y prime equal lambda y, that will be then, the y will be equal to some initial condition that we have. In our case, the y0 would be the difference. The y is between z tilde 0 and z0. The difference in the initial condition will be the y0. And the solution is then that initial condition times e to the lambda t minus t0. If you try that, take the derivative, then you will see that you will get lambda times y, and then you see that this equation for j equal lambda is fulfilled. And now you can easily see what that means for the stability of the ODE. The ODE is stable for the real part of lambda smaller than 0. Because what we look at is when the time goes to infinity. So we get a large time, and then if we have here something that has a negative real part, that is then determining essentially the absolute value of that. The imaginary part is only, absolute value of that is just 1. So the real part is the important, and if that is negative, we have e to something negative here, and you know the e function goes then to 0. So then we have that the solution, this solution goes to 0 as we let the time go to infinity. And then we say that the ODE is stable. On the contrary, if the lambda has positive real part, then the absolute value will explode. Then this goes to infinity. The exponential with a positive lambda goes to infinity as t goes to infinity. So then the ODE is unstable. The real part greater than 0. Then we see that the absolute value of y goes to infinity for t to infinity. And the final condition that we might have is that lambda is 0. If lambda is 0, then we see here, we get here then e to the 0 is 1, we get y is equal y0. So then we don't move away from the initial condition. So that is called neutrally stable. So ODE, neutrally stable for the real part of lambda is equal to 0. So we might have also some, if we have something else, we might have some variation, but the absolute value will stay constant. So that will be actually the absolute value of y0 for t to infinity. So that means we can then characterize the behavior of the ODE. It's called also asymptotic behavior, that is when t goes to infinity, by looking at the eigenvalues of the Jacobian. And it turns out for numerical methods, we can do a similar thing, and then the equation that is really most important to us is then this equation in the scalar case when this is lambda, y prime equal lambda y. Like here, the discussion that we did here for the scalar problem, that is then also valid when we do the analysis for the numerical method. So then we argue that stability Now we have here to explore the ODE, or the ordinary differential equation. Now we move over to the stability of a numerical ODE method. So a method to solve an ODE numerically. And it turns out that it can be analyzed in much the same way as we did it here for the scalar problem. And this equation has a name that is due to the mathematician who investigated that first. That was German Dahlquist from KTH. That is actually this equation. Then we have 2, now I have the cubes 3 here. Y prime is equal to lambda y, and we assume that lambda is complex and that it is simply constant. And that we have an initial condition at t0 equals 0, which is 1. So the solution to this, if we look the exact solution to this, then we would have here this situation. This would be 1, this would be 0, so e to the lambda t. That would be the exact solution to this. So now we define the stability of an ODE method in the following way. If the numerical solution of the test equation 3 yn stays bounded, so we are very moderate here, so we just require the solution to stay bounded. And now the equivalent to t going to infinity is now letting the time level go to infinity. We silently assume here that we have some constant time step, so that we can do the analysis. So then, and bounded means we have some number for which all the yns are naturally smaller, equal that number. So that is clear. Then the numerical method that we use to compute this yn is called stable. So now the stability is related to the behavior of the numerical approximations yn for n to infinity to have that bound. I can give some number for which this is smaller equal. Now we want to check that for Euler's method. What does that mean for Euler's method? And there we had Euler's method, we had yn plus 1 that we derived yesterday. That is yn plus, now we assume that we take the constant grid spacing h, constant time step, times f of tn yn. So that is Euler's method. And now we want to apply this to the test equation. For equation 3, we get then, that is 5, we get yn plus 1 is equal yn plus h. What is the f? So what is the f of t and yn? This is our f of ty. We have no t dependence, only y dependence. So f of t and yn is simply lambda yn. So we can factorize the yn and get 1 plus, I write the lambda in front, lambda h yn. So we get this relation to get from time level n to time level n plus 1. The numerical approximation is such, for the test equation, we have to multiply by this factor. Now we can go to yn minus 1 and so on. We can go all the way to 0 and 0. When we do that, we get then a formula how to express the numerical solution by Euler's method for the test equation in terms of the initial condition. So we can apply this formula recursively. The 5 implies following, that we get, now we start with yn, it's easier. But each time we go one step before, it means multiply by this factor. So to get to time level n, we have to multiply with this factor n times. That means we get 1 plus lambda h to the power n times y0. But we had assumed that the y0 was 1 from Darcy's test equation. So then we get that this is 1 plus lambda h to the power n. So then we get this relation for the numerical solution of the test equation using Euler's method. We get this. And this factor that we got by just doing one step, that is called, as you see here, amplification factor. We get every time step, the solution gets amplified by this factor. So then we can say the amplification factor, I give it a name, I call it g of lambda h. We define it by yn plus 1 divided by yn, or you can take any, or yn divided by yn minus 1, doesn't matter. That is called amplification factor. It's called amplification factor. So that is now a general definition, and we can use that for Euler's equation, for Euler's method. Euler's method, the amplification factor is g of lambda h. Then we have it, can get it from here. The ratio of the new divided by the old solution for the test equation is equal to 1 plus lambda h. And now we can imagine what we need. We need that this amplification factor, as we go on, that the solution with that will be yn is the amplification factor, that's the general form, to the power n. So that will be the general solution. Here this is for Euler's method. But the general formula would be that yn is equal to the amplification factor to the power n. And that we want to have bounded. So for yn, absolute value of the numerical solution to stay bounded for n to infinity, we need that the solution, which is then the solution then is, as we now generalize, it is the amplification factor to the power n. That will be the general solution. That has to be bounded. So that is now the general. We have started with Euler's method, but in between we have generalized this. And we have also seen when we have this problem, it means that we get the solution to the test equation. In one step, it is the amplification factor, and that is to the power n, the solution at time level n. And that has then to be bounded. What does that mean? It means that this amplification factor in absolute value has to be smaller than 1. If that is the case, you can then multiply any number by smaller than 1 by power n, and you let n go to 0, then that will go to 0. So the condition is that the absolute value of the amplification factor is smaller than 1. Then it will actually go to 0. So then we can use that to define stability. So that is actually then the stability condition that we get from that. So from that we get then the stability condition. Then we're now at 8. If the absolute value of g of lambda h, which is our amplification factor, absolute value, is smaller than 1, then we go to 0. But if this is 1, it stays 1. That is good enough because we just want to have it bounded. So we can allow here also for equal 1, smaller than equal 1. Then the numerical ODE method that we use is stable. We'll see later on in an example what it means when we just choose the amplification factor equal to 1. So smaller 1, that is really the safe, but 1 we can allow because we only require a bounded solution. It need not go to 0. But if it's smaller than 1, then we will go to 0, ultimately. So, and if we have the amplification factor of the numerical method greater than 1, then the numerical ODE method is unstable. We shall see also, and you can do experiments with that yourself, that you'll see that sooner or later. And it is just, if you violate the condition just a little bit, it takes a little longer, but you'll see it can be quite violent. So, let us see what this means for the explicit Euler method. No, we call it Euler's method. Explicit is also a name used by Euler's method. Euler's method is then stable if that is then the condition 9, the absolute value of the amplification amplification factor G of lambda H that we have derived just before to be 1 plus lambda H, that has to be smaller equal than 1. That is the condition. So that we had derived before, that the amplification factor, ratio of the numerical solution for the test equation at level n plus 1, divided by the solution for level n, we got this. Absolute value of that has to be smaller equal than 1. So that is our stability condition for the for Euler's method. And there is another way to say that. So then we can find out for which values of lambda H this is true. And that is then equivalent to saying, this is condition 10, that the lambda H, the lambda coming from the test equation, and the H, the time step, that is inside a certain domain, which we call the stability domain. And for Euler's method, it is the domain consisting of all the complex numbers for which the absolute value of this number, minus 1, is smaller equal than 1. Can we see that? So if lambda H has this property, for example, lambda H, let's see, this is actually wrong, because we need it has to be at, needs here a plus, right? It's because if z is equal to minus 1, we would get a minus 2. This is wrong. This has to be a plus, sorry. Because it has to be around minus 1. So if z is minus 1, that means if lambda H is minus 1, we put it in here, we see we get 0. So this domain what we have here is the following. We can now draw this domain, and that is called the stability domain. This is the real part of the lambda H, and this is the imaginary part of lambda H. Remember, lambda is coming from the test equation, it's a complex number given to us by the ODE, and H is the time step. So we can then look for all the lambda H which will fill this, or it turns out it will be these. So we have already seen lambda H minus 1 is a very good candidate. We can also take lambda H equal to 0. We can also take lambda H equal to minus 2. Minus 2 is 1, minus 2 is minus 1, absolute value is 1. So, and if we use the complex numbers that have an origin at minus, so this is minus 1, and which have a radius of at most 1, we will get a circle around minus 1. So we have here the minus 2, and the circle has a radius of 1. So all this in here, that is making up S, the stability domain. So that is S, and that is the stability domain. In that case, in this example, it is the stability domain of Euler's method. So instead of then doing it in this way, that we say we want to check whether the amplification factor in absolute value fulfills the condition that is smaller or equal 1, we can check whether lambda H is inside the stability domain. That is equivalent. Because any number that is in here that will be the z that will fulfill this, that will be minus 1 plus will be e to will be e to the phi. That is, what is that? potential. Let's see. Can have any number. Let's see. Can do that. Let's see how that goes. Then we would be on this circle here. And then we can even have some factor in front, say r, and so the r would be smaller or equal than 1, and the phi can be any number. So then we can represent every value inside this circle. And for any value of that, we will be inside the stability domain. So that means lambda h can be of any form like that. But if lambda is real, then it must be between 0 and -2, right? If lambda is real, then we have only this chance. Then we cannot go into in the imaginary part of the complex plane. We are then on the real axis. Then it must be between 0 and -1. So let's take that as an example. Now we take an example where lambda is just the real number. Take the example that I showed yesterday to illustrate the local truncation error and the global error. It was y prime is equal -5y. Now we take the initial condition simply to 1. So that would be then our equation 11. In this case, we have the lambda is a real number, -5. And then the stability condition for Euler's method, number 9, becomes 1 plus lambda h, absolute value in our case is then 1 minus 5h. That has to be smaller or equal than 1. And now we are real. And we can express this condition in the following way. We can say that this is equivalent to saying that this number has to be between -1 and +1. Then the absolute value is smaller or equal 1. So then we have -1 smaller equal 1 minus 5h smaller equal than 1. That is equivalent. And then we can see when is this condition fulfilled. The right inequality is easy, because h is the time step that has, of course, to be positive. If that is positive, we get here something that is smaller than 1, actually. So this is okay, this inequality for h greater or equal to 0. And that is a very natural condition. The other condition is more interesting. So it is this condition here that we can express also in a different way. So we can order this equation. We can take the 5h to the left and the -1 to the right. And then we see that this is equivalent to saying that h is smaller or equal than 2/5, which is 0.4. So if we have this condition fulfilled, then the left inequality is true. So from that, we see that the stability condition that we get is that Euler's method is stable for if both conditions are fulfilled. H has to be smaller or equal to 0 and smaller or equal greater equal 0 and smaller equal 0.4. So that means we have this condition that 0 smaller equal h smaller equal 0.4. So that is, we get a number, a real concrete number. And we see that depends then on the lambda. If this, we would not have minus 5, but minus 500, for example, it would get in here, so this would be much lower. So the higher the lambda coming from the ODE, that would give us then the smaller time step. We shall see that next week when we look at so-called stiff problems. Then we have this situation that we have to really choose very small time steps because of that. So, but here we have this, and now we want to see how this affects the solution. So now we solve this problem, this test equation, by Euler's method. And we use different time steps for that. So h, you see here, I have to enlarge it, is 0.1. So I have not given the exact solution, I've just given the numerical solution. But we can imagine that this is probably, well, not a too bad representation of what is actually happening. We have some numerical error, so we give the initial condition 1, and so on. And that is done with this time step 0.1. So, that was the wrong button I pressed. Let's see. This is now with the time step 0.2. That's a special time step because then after one time step we go to 0 and we stay on 0. Because the amplification factor 1 plus lambda h, that is in our case, it will be the minus 1 here. Let's take that. So we will have our amplification factor that we have in our case is 1 minus 5h. And if the h is 0.2, we get 0. And then the amplification factor is 0. So then we get the solution 0 after one time step and it stays there. So this is not correct, but it is at least stable. Let's see. This is the condition when we have the time step almost 0.3. So it is adjusted so that we hit the end time, which will be at 10. And you see we get some oscillations in the beginning, but the solution recovers and stays stable. And now here we have the case when we are just on the stability limit. We said we can go up to 0.4, and that is what we chose here. So we get oscillations, but the solution stays bounded. So we would accept that as a stable solution, but it would not be a good solution, because this is far off the exact solution. And here we have now the example when we have violated the stability condition. We have gone beyond the limit. It is 0.5 here, the h, and you see what happens. Look at the scale. We have a solution here, we should have a solution that is smaller equal 1. And what we get here are values larger than 3000. So this is an instability, a numerical instability. So here you see what happens when you violate the stability condition. It explodes. And if we would do that here with 0.41. We would have to go longer in time to see it, but it would happen if you would get an instability. So this is dangerous. So we have to observe this. This is critical. Okay, so you can play around with that yourself, but we stop here to allow the people from green technology to get to that. So then we have seen already here some insight into relate here the stability of ODEs, and this example shows the importance. Next week we'll continue with that. Also we'll look at implicit methods. The methods that we saw today were all explicit methods. You can again get from the old time level to the new one without any problems, without solving any linear or nonlinear system just easily. But nonlinear implicit methods are more complicated, but they might be needed if the lambda gets very large, if we get so-called stiff problems. Okay.